In this video, we will be looking at the series of reactions that are all known as nucleophilic addition reactions. So when you learn the nucleophilic addition reactions mechanism, you can apply that mechanism to synthesize many different types of compounds as is covered in the chapter. What is the nucleophilic addition reaction? As you know, carbon in a carbonyl group is electrophilic. And since it's a electrophilic carbon in the compound, then any nucleophile can attack the carbon. The nucleophile could be a strong nucleophile or weak nucleophile. That's why when you look at the mechanism of different types of compounds that are made by nucleophilic addition reactions, sometimes the nucleophile directly attacks the carbon, and sometimes in order to get the carbon susceptible for attack, you need to acidify the solution. So basically what is happening in here, like in this example, you have electrophilic carbon in here, the nucleophile comes in, okay, and attacks the carbon, and as you know, there is a pair right there that is going to shift on oxygen, and when that happens, then you get an ion that is known as alkoxide ion, and we have seen this many times in many reactions that we have done in the past. Then when you have alkoxide ion, the oxygen right there is basic oxygen. Then if you have something with the proton in the solution, then that oxygen can get a proton from whatever you have and to give whatever the type of compound that you're trying to make. Right? So that's what really nucleophilic addition reactions are, and this type of reactions can happen with aldehydes and ketones. Aldehydes in general, they do this type of reactions much better than ketone, and depending what kind of ketones you have, some ketones they do it better than the other ketones, and the reason is because of the steric hindrance that you're going to have in here when you have different groups on the carbon. Here we are looking at a nucleophilic addition reaction, which the nucleophile is a Grignard reagent. As you can tell that since this R group has a lone pair with the charge, is going to attack this carbon, which is partially positive, then the pair between carbon and oxygen is going to shift, and you're going to get this alkoxide ion. So as soon as you have water or you acidify your solution, you're going to get an alcohol. And this is something that we learned when we were learning about how to synthesize different type of alcohols. We use Grignard reagent and treat Grignard reagent with aldehydes and ketones, and we made a secondary or tertiary alcohol. Here is another reaction, and in this reaction, the Grignard reagent, we are not using Grignard reagent, we are using sodium borohydride, and as you know, sodium borohydride is a good source of hydride. So the hydride, meaning hydrogen with a lone pair and a negative charge, is going to attack that carbon, and when it attacks that carbon, again it forms alkoxide ion, and all you need is something, like I said, with the acidic proton in the solution, so this oxygen can act basic and get out a proton from whatever you have in the solution, in this case ethanol, then to give you an alcohol. Okay, and this alcohol, when you look at it, is a secondary alcohol because a hydride is used. As it was mentioned before, both ketones and aldehydes can do this nucleophilic addition reactions. Now the question is which one does better than the other one. As I mentioned earlier, aldehydes in general, they do nucleophilic addition reactions faster and better than ketones. There are a couple of reasons. One of them is that in aldehydes, this carbon is more electrophilic than the carbon in ketone. And when the reaction is done, the product, if you look at the product, in the product that you get from a ketone, you have more larger groups around the carbon, and in aldehyde you have one large group and you have hydrogen. So here is less crowded. It means there is a less steric hindrance. Here is more steric hindrance. That's why when we look at this type of nucleophilic addition reactions, they all have this equilibrium issue that reactions can, is reversible, can go back and forth. But in case of aldehydes, when aldehydes, they do this type of reactions, the equilibrium is favored toward product more than it is in case of ketone, and that is because of the steric effect that you have in the product. I've already said that the aldehydes are better than ketones in this type of reactions. Now there is a question, how could we even make them better to do this type of reactions faster? One thing that you can do is to add electron withdrawing group in your R groups that you have in here. So the more electron withdrawing groups you put in the chain, then it means the reaction is going to go faster and you're going to get more product. Like if you look at the example on page 904, problem 18.14, that's what they are really doing, is they are ranking different type of aldehydes and ketones in terms of which one of them is better for nucleophilic addition reactions. And the way you figure it out is like which one of them has more electron withdrawing group and which one of them has that electron withdrawing group closer to this carbon. Here is another example of a nucleophilic addition reaction of ketone and aldehyde, and is known as hydration. Basically, hydration means that you add the water molecule to this carbonyl carbon, and you're going to get the diol, and the diol is known as geminal diol. So when you look at it, really compare this structure with that structure, you see that the difference is the water molecule. And remember, aldehydes, they do this type of reactions better than ketones. And when you look at this example, which is about the ketone, you will see that the equilibrium constant is very small. So it means the reaction really is favoring the carbonyl compound. In this case is acetone or ketone. So you can do the same reaction with aldehydes and get the hydrate, and then the equilibrium constant for aldehydes would be bigger than it is for ketones. Here is an example of nucleophilic addition reaction in which the nucleophile is a weak nucleophile. In this case, is water. So for hydration, which is changing ketone or aldehyde to a diol, we need to use water. And if you are going to use water, this is called acid-catalyzed nucleophilic addition reaction, is because the water, as you know, is a weak nucleophile, and in order to make the water a better nucleophile, then we have to make our solution acidic first. So when we make the solution acidic first, it means we are changing this oxygen to this form in here. As you can tell, this is there's going to be positive charge. So there is a positive charge right there. Then it means it's going to withdraw more electron from this carbon and make this carbon more electropositive than it was right there. So when this carbon is more electropositive, then it means the water can attack this carbon easier. And so the water is going to attack, then it's going to form a bond right there. And we have seen this situation here many times in many reactions. As soon as you get oxygen with a positive charge with hydrogens on it, you can remove a hydrogen using what you had in the solution already. So the water is going to take this hydrogen, and then this pair is going to shift, and we're going to get hydrate. Now, you could do the, like I said, same reaction with the aldehydes, and you're going to get the diol, and you're going to get more product for, hydrides that are formed from, or diols that are formed from ketones, aldehyde.